here you can find some information which quantifies that Egypt consumes about 80% currently of the Nile waters, and Ethiopia has a negligible consumption in the present state, even though you see that about 85% of the Nile waters comes from the Ethiopian highlands. So you can really see that the Ethiopians have a lot of points in claiming the usage of part of the water, and while Egypt uses about 85% of the water. And you see also the history of the agreement. So in 1951, an agreement was signed between Egypt and Sudan about the sharing of the Nile waters. And basically in these agreements, the Ethiopians were always considered as not very relevant. So this is another reason why now the Ethiopians claim that now it's their time to be able to exploit the water resources of the Nile River. And here there are other information, and the Nile Basin Initiative, which I already mentioned to you, and it was established when the project first was launched, and then there were boycotts from some states. They didn't want to participate in the activities because, of course, when you feel that you are called to form a body and some countries have the minority, they may decide to boycott the initiative because, of course, otherwise it becomes they may prefer to boycott instead than losing. Now let me mention to you that evapotranspiration, as I said, it's a problem. Siltation is also a relevant problem because even if the dam is very huge, you know that the lifetime of a dam is unfortunately limited. And the lifetime is limited not just for the structure of the dam. The structure of the dam would last much longer than the reservoir capacity, and therefore reservoir capacity gets depleted quite quickly. And basically when one designs a dam, an optimistic view would predict a lifetime of about 100 years. And this is probably the longest time that a dam can be assumed to be efficiently operating. There are cases, unfortunately, where the reservoirs got silted in a much shorter time, like 30, 40, 50 years. And of course, there is also uncertainty here because there is variability in the flows of the Nile River. So any decision that one takes is affected by uncertainty because the river flows may be lower than expected. There is also climate change that may impact the river regime. And therefore, this is a typical case in which utility theory applied by involving the politician, by involving, of course, the stakeholders. In these cases are politicians, are the people that have the responsibility of driving the policies for these countries. And this is a case where utility theory can be successfully used as well as pairwise comparison. And there are many examples like that. I decided to talk in detail on the Nile River because there is this now this dam, which is relatively close to us, that is that now is entering into operation. But there are many examples like this. A very known example is that of the Jordan River that is mentioned here. And you may remember that there were wars between the Jordans and the Palestinians for the use of the water of the Jordan River. And then there are several rivers in China and Vietnam where I mentioned to you they are building very huge dams which again need a careful evaluation of the impact. In this case, this dam is, as I said, the capacity is around 70, 80 billions of cubic meters, let us see as another example the Three Gorges Dam in China. Just 1 second. Let's see if I can get the connection back. Otherwise, you may Google it, and you will see that this is another example of a very huge project. Even in this case, the dam was finished about, I think, 10 years ago, and they are still filling it. Okay, should work. Maybe that I already showed to you the Wikipedia page. I'm just interested in showing you the main details. And the main purpose is, it's an hydroelectric dam, but they also use it for irrigation. And you see the construction cost, 26 billion US dollar. And I just wanted to see the capacity, to make a comparison. The dam is the largest operating hydroelectric facility in terms of annual energy generation, and it's the world's largest power station in terms of installed capacity. And so the project was completed and fully functional in 2012, which means that probably they finished to fill the dam there. And dimensions. So the height is about 180 meters, and yeah, you see here the storage is still lower of the Millennium Dam. So it's the largest power plant in the world, but it's not the largest reservoir. Okay, this is another example which is very interesting to see. Now let me now move to the technical details I was mentioning to you. Here, a relevant problem was, and I say that it's relevant, but indeed it was relevant during the construction of the dam. And I know this problem because I told you that the dam was designed by an Italian company of professional engineers and was built by an Italian company, the Salini. They built the dam, and this company of professional engineers designed it. So we were called, these are based in Rome, we were called to solve this problem, I mean me and my co-workers, of the estimation of the seasonal flood frequency distribution. What is the problem here, basically? The problem is that during the construction of the dam, you run the risk of getting flooded. The works run the risk of getting flooded. And you have to build diversions of the river flow in order to be able to work on the river bed. And these diversions are designed to carry downstream, of course not the flood flows, because otherwise the diversion would be impossible. They are designed to carry downstream, let's say, ordinary flows. And then if a flood comes, of course the diversion doesn't work anymore, and the water goes back to the riverbed, and the works get flooded. And this is not a problem for the human life, because in a huge river usually you can predict the flood in advance, so you can leave the construction place, but it's a problem in terms of economical damage. And therefore this means that the more strategic in economical terms works should be planned in the season where flooding is less likely. And therefore, in order to plan the construction works, one needs to get an idea of the distribution of the flood frequency in any season, so that, of course, you may plan that when there is the highest risk of flood, you have completed the most delicate works, those that you cannot tolerate that they get flooded. And therefore it is extremely important to try to estimate the flood frequency distribution for each season. And this is the river regime for the Nile. And this is dominated, the climate is dominated by the monsoons, and therefore it's a river regime with only one maximum. You see that you have only one peak, which is in around September, end of August, September. And here you see two lines, because basically the black one is the mean daily stream flow, and there is the standard deviation, which is given by the red line. So basically you get an estimate from the black line of the average of the river flow in any season, and from the red line you get an estimate of the variability. So average plus variability, you get an estimate of the likelihood of getting a flood in the given season. Usually, in the flood season, you have a higher average, but also a higher variability, which means that, of course, the probability of getting an extreme value is much higher, because you start from an average level that is higher, and you have also a higher variability. And this is clearly reflected by these observations here. And annual maximum series are reported as blue dots. And you may say, what's the difference? The difference is that the black line comes from a measurement that is taken through a particular instrument that works continuously. The dots are observed through another instrument that is able to get only the annual maximum, and with the date in which the annual maximum occurs. And basically, in order to get the dots, you don't need a complicated instrument. You just need to look at, on a certain reference, like a wall, what is the water level, and then you can easily see what was the maximum. You know the day of the year in which the maximum occurred, and then you just need a transformation function from the water level to the river flow, which is usually estimated through hydrological analysis. So basically, these are two different ways of measuring the river flow, and basically we have two different ways because there are different entities that measure river levels, especially for an important river like the Nile, and therefore you may get different information, even for the same variable. And when you get additional information, this must always be used. Remember that in order to reduce uncertainty, you have to increase the amount of information. And you see that here there is a fair agreement. And you may wonder why the blue dots overestimate the daily measurements. The reason may be, first of all, a different instrument may be biased, and therefore there might be an overestimation or underestimation by one of the two instruments. Another reason could be that the maximum is measured very often it's measured in a different way with respect to the daily river flow, because the daily river flow is measured as an average along the day. The maximum is the measurement of the instantaneous maximum. So one may expect that the measurement of the maximum is higher than the estimate of the daily river flow. Indeed, there is to say that for a large river like the Nile, I would expect that they are very close. But for short rivers, for small rivers, you may understand that the maximum is much different from the daily average, because for small rivers you have a very rapid evolution of the flood. Now the question is, okay, we have this data, how should we estimate the flood frequency distribution? Because we know how to estimate, if you took some background of hydrology or some background of in civil engineering of hydraulic works, you know how to estimate the annual maximum flow for a given probability. Basically, this is standard and classic assessment that is done in hydrology. If you have a data set, it's very straightforward. We don't go into the details in this subject, but it's very straightforward to estimate the probability of occurrence for the annual maximum. But when you turn to the seasonal maximum, the situation becomes more complicated because, and I give you a reason for that. You may understand that when you put together 4 seasons, you have to get back the annual maximum. So there is a constraint that you need to put on the overall process, that the highest flow from the 4th season gives you back your estimate for the annual maximum. And this is what we did. Basically, this was something that was not really treated in the literature, how to impose this constraint. And we did this evaluation. I'm not going into the details of this plot, but basically here you see the discharge on the abscissa depending on the return level, return period in years on the ordinates for different seasons. And basically we identified 4 seasons and what we call the dry season, a pre-flood season, a flood season, and a post-flood season. And then we checked that by taking the maximum from each of these seasons, we got back the probability distribution of the annual maximum. This is the study that we did. And actually, we were a bit lucky because during the construction of the dam, which was completed in 2012, it seems that they didn't get flooded, and therefore they were very happy. So that is indeed something that was really interesting. To give you an idea, this was an evaluation that was carried out by about 1 person full-time for 6 months, plus supervision by a couple of professors, and the amount of money that we asked for this work was 25,000 gross euros. So it's not really a big amount if compared with the cost of this dam. And do you remember how many billions? And meaning that, you know, sometimes there is a false convincement that when you ask the advice of scientists or university professors, they are very expensive. I don't think that in this case. Later on, they admitted that it was very effective and cheap. So basically, this is a detail that I wanted to bring to your attention, just to give you an idea, because it's also interesting to have an idea of how much one may ask for a professional work. And of course you have, in some cases, the Association of Professional Engineers give you guidelines for determining the cost of your job, of your work, of your consultancy. But there are some situations which are not usual, like scientific research or innovation projects, where basically it's subjective, determining the amount of money that is needed for carrying out the work. Okay, for this example, this is fine. One thing that I want to introduce, because we are going to speak on this topic on Friday, but I would like to introduce it now because it's important and I may need some time, is climate change. When you carry out this kind of evaluation, like estimating what is the optimal design for a dam, what is the expected peak flow, how to devise a water resources management policy, you always get trapped into the climate change problem. Because during the discussions, climate change is pointed out by the stakeholders. And what's the reason why climate change is always mentioned. You may say that the reason is obvious, because it's there. You may say it's there, and therefore people are concerned. Indeed, the reason is much more complicated, because no doubt the climate is changing, and there is no doubt on that. But on the other hand, climate has been always changing. We know that in the past we had glaciations, and therefore it's clear the climate is changing and always changed. And the changes that we had in the past were very relevant, I mean. So we shouldn't be surprised, we shouldn't be astonished if we experience some climate change. And therefore, for sure, climate change is there. However, I can tell you that as far as I am concerned, in the evaluation that I'm carrying out when I apply water resources management in practice, the real impact of climate change on water resources availability so far, and I'm speaking in particular for Europe, but with some exceptions this can be extended worldwide, and I will tell you what are the exceptions. The real impact so far is negligible in terms of impact on the design. So basically, if I try to account for climate change, projected climate change, into the design process of a dam, I end up with more or less the same results. So basically, a little bit changed, of course, but not so significantly to justify the concern, the growing concern of people, and to justify that this concern is more relevant than the concerns related to water pollution, for instance. I think that water pollution is really a concern, and in my view, it's much more concerning than climate change. But on the other hand, if you ask people what is the main problem for water resources now along the street, 80% of them, they will say climate change. They won't say water pollution or increasing population. This is another big problem on water resources management. We have increasing population and increasing demands. Increasing demands because people, with the increase of the societal benefit, they ask for more water. And this is a legitimate request, fully legitimate. 100 years ago, people were used to take a shower once in a week on average, and today people take a shower every day, and this is perfectly legitimate. On the other hand, the increased demands and the increasing population are really threatening the sustainability of water resources for the future, as well as water pollution. And I would say that climate change is a concern, but not as concerning. This is what I can see from the numbers. When I experience problems, the problems are not given by climate change. The problems are given by increasing demands, increasing population, and therefore more and more demands, and pollution, so that you can't use surface water anymore because the river is polluted, and then you have to use groundwater, and groundwater is a problem because you need to pump it and you really don't know how much water is there. So what is the reason why climate change is a real matter of concern? It's a real matter of concern because it's not just limited to water resources. It's a concern related to everything. And also it's concerning because the scientific community gave the feeling that we may get quickly to an irreversible situation where climate could change very rapidly in an irreversible way. So basically the concern due to climate change is this possibility. The possibility that we get to a stage where the situation could reach a tip point, it's called, where you get a flip. And the flip could imply that, you know, it's no more reversible, and from a stable equilibrium you get to an unstable equilibrium, and then to a fully reversal of the climate, like the inversion of the magnetic field. You know that there is, it happened in the history of the Earth that the magnetic field suddenly got reverted, during no more than, people say, no more than 100 years, which is like instantaneously for the life of the Earth. So basically, some people say, okay, like the magnetic field for some reason got suddenly reverted, also the climate could experience a shock. And the shock may imply whatever, very dangerous situation that could bring us to a mass extinction. And this is why people are very concerned. In my view, I don't see this problem as a water resources management problem. So basically, when we are involved and called into play for designing a dam, the fact that climate change is brought to our attention, in my opinion, is an unfortunate situation if it distracts the designer from the correct evaluation of the real problems. So this is what I wanted to say. And in order to be more detailed, there is what is the evidence of climate change today. The evidence is an increase of the global temperature. This is an evidence. And this is an evidence that is unquestionable. And it's also testified by the retreat of the glaciers in Europe. There are some glaciers all over the world that are advancing, but very few of them. There is a retreat of the polar ice, a retreat of the glaciers in Europe, and this is due to the increase of the global temperature. Keep in mind that we are talking about an increase that started about around 1850 and reached the peak around 2004. In the last 10 years, the temperature has been quite stable. There was a claim recently by the NASA that the 2014 was the warmest year forever. And this is a statement that is not supported. If you Google, you find a lot of information. The temperature, the global temperature in the last 10 years has been quite stable. And the reality is that we don't understand these processes. Even if we try to build climate models for predicting the future, the reality is that the climate system is very poorly understood. We don't understand what regulates, what caused the glaciations, and we don't fully understand what is the reason for this global warming. It may be the increase of CO2, the concentration of CO2, but this is a bit controversial because if you raise the temperature of the atmosphere, a direct consequence is that the ocean increased the emissions of CO2, and therefore the CO2 could be increased because the temperature increased, not the other way around. It's not clear. They are strictly connected. CO2 and temperature, they are strictly connected, but it's not clear what started first. And, but it may be, indeed, the increase of CO2 from human emissions could have caused the raise in global temperature. But if the raise in global temperature is unquestionable, there is no evidence of tendency in the rainfalls. So you see in some regions of the world and some regions of Europe where rainfall increased, and there are some other regions, even in Europe, where rainfall decreased. There are hotspots which cannot be clearly explained. In the Alps, the temperature increased more than globally, and it's not clear why. So the Alps are a hotspot. And the increase of the global temperature is about 1 degree from 1850 to today. So 1 degree in 150 years. It's not much credible when people say, I can feel global change, I can feel the increase of temperature. This is not much credible, because if you look at the past 40 years, the temperature increased about 0.2 degrees globally. And so it's not much credible when people say, it's fine if people realize that the amount of snow is reduced, even in this case, there are some years where it's not so evident. But this may be fine, because an increase of temperature of half a degree could imply a substantial decrease of snow in some regions. But for sure, the effect of rainfall, there is not a clear tendency. And also in terms of river flows, if you look at river flows, you cannot distinguish if the changes were caused by human withdrawal rather than climate change. I spent a lot of time trying to inspect the series of the Po River, where people say that it's clear that there is evident the effect of climate change. I couldn't see it. And I looked at the number, I can tell you, not just perception. I just went to the numbers and tried to understand what's there. For instance, in 1940, there were 10 years where a very long drought over the Po River. Why? Nobody knows. But it's clear that there was a drought, people still remember, and lasted 10 years. So, basically, this is my introduction, and I would like to continue to speak about climate change because it is extremely important for a water resources manager, and it's extremely important to get an unbiased view, and it's almost impossible. If you try to Google climate change, you get millions of entries, and you see a lot of contentions, a lot of claims, and a lot of disputes, legal disputes. You may have heard about the climate gate that it occurred about 10 years ago, 7 years ago. So it's really difficult to get an unbiased view. I would like to spend some time speaking with you because this is my target, to try to provide, as far as I can, an unbiased view. Okay, PC on Thursday. Thank you. Just turn off the